Welcome, NOAA Science. Tonight, the story begins on the first days of spring, when the United States should be easing into a gentler season, yet the atmosphere behaves as if summer has arrived far too soon. Across the southwest and Great Plains, temperatures climb into dangerous territory, forecasts struggle to keep up, and dry winds turn vast grasslands into a landscape ready to burn. Above it all, a stalled jet stream and a rare upper air pattern create a heat event so unusual that scientists are forced to ask deeper questions about what the atmosphere is becoming capable of. In this documentary, the focus stays on the real science behind the heat, the fire risk, the failing forecasts, and the larger pattern holding it all in place. Before we begin, please like this video, subscribe to NOAA Science, and leave a comment sharing where you're watching from. Now, the full picture starts to unfold. Across the United States, the event takes shape first, not as a list of local temperatures, but as a single continental arrangement of air, pressure, dryness, and motion. The atmosphere over the country does not behave like a set of separate rooms. It behaves like one connected structure whose parts lean on one another. Warmth in one region is tied to sinking air in another. Dryness over the plains is tied to the same broad pattern that bends storm tracks away from one side of the continent and drags colder air into another. In this case, the first scientific fact that matters is scale. The event is large enough to span much of the nation at once, and that changes its meaning. A hot afternoon in one city can be explained by local terrain, local winds, or a temporary shift in cloud cover, a pattern that warms the southwest, dries the Great Plains, redirects storms toward the northwest, and sharpens temperature contrasts across thousands of miles belongs to a different category. It becomes a continental circulation event, and the atmosphere has to be read as a whole. At the broadest level, the country sits beneath a distorted upper air pattern in which the usual west to east flow loses some of its smoothness and becomes deeply curved. Meteorologists often begin with this upper pattern because it organizes the rest. Air high above the ground moves in a corridor of strong winds that helps separate warm and cold air masses and helps weather systems progress across middle latitudes. When that corridor bends sharply, the consequences spread over enormous distances. One part of the continent may sit beneath rising heights and sinking air, which tend to support warmth, clear skies, and persistent dryness. Another part may sit beneath a trough, a southward dip in the pattern that favours cooler air, unsettled weather, and a different set of surface conditions. The result is not weather that is random or scattered. The result is weather that is internally connected, even when the surface experiences seem opposite. This is why 1 week can contain desert-like air over the central plains, heavy rain farther west, and colder air intruding into distant regions. The atmosphere is not contradicting itself. It is expressing the shape of the larger flow. In this event, the western and central parts of the country lie under the influence of a large ridge, which is an elongated zone of higher pressure aloft and higher atmospheric thickness. Thickness, in weather science, refers to the vertical distance between pressure levels, and that distance grows when the air column is warmer. Warm air expands. A thicker air column is one sign that the atmosphere is storing more heat. Beneath a strong ridge, air tends to sink slowly. As it sinks, it compresses and warms, and cloud formation becomes less likely. With fewer clouds, more sunlight reaches the surface through the day. Over time, the land absorbs that energy and the lower atmosphere warms further. The process is not dramatic in appearance. It is quiet, steady, and cumulative. Over large dry regions, the warming becomes even more efficient because less of the sun's energy is spent evaporating moisture. More of it goes directly into heating the surface and the air touching it, This helps explain why the broad middle of the country can begin to behave like a giant heated plate when the pattern remains in place. Yet this event is not only about heat, it is also about contrast. A continental weather pattern becomes especially significant when it creates sharp differences over long distances in a short time. That contrast tells scientists that the flow aloft is strongly amplified, meaning its northward and southward bends are pronounced rather than gentle. In a flatter pattern, air masses move along with less extreme separation. In an amplified pattern, warm air can surge unusually far north while cold air can spill unusually far south elsewhere. The nation then experiences not one smooth seasonal transition, but a stretched and uneven distribution of atmospheric states. Regions that should be moving gradually into spring are pushed into very different regimes depending on which side of the upper air pattern they occupy. The map, viewed this way, begins to look less like a patchwork of forecasts and more like a structural diagram. The important feature is not just where the hottest reading appears. The important feature is how many related outcomes emerge from the same atmospheric architecture. Over the western interior and into the plains, warmth spreads beneath the ridge. In the central drylands, low humidity intensifies as descending air suppresses moisture and strong mixing draws dry air downward. In other parts of the country, the same distorted flow favours storminess, colder intrusions, or lingering unsettled conditions. Each outcome differs at ground level, but each belongs to the same frame. That frame matters because continental events tend to persist longer and produce deeper impacts than isolated local anomalies. Local weather can reverse quickly when a sea breeze develops, a weak front passes, or clouds increase for a day. A continental pattern, by contrast, has inertia. Its size gives it durability. It takes more than an ordinary daily fluctuation to dislodge it. That durability allows consequences to accumulate. Heat builds over land already exposed to sun. Vegetation dries after repeated afternoons of warmth and wind. Nighttime recovery weakens when the broader air mass remains warm. Forecast errors can also grow more meaningful in such a pattern because the same broad setup influences many stations at once. A repeated underestimation across a large region signals that the mismatch is not trivial. The atmosphere is behaving in a way that exceeds what the forecast framework expected over a wide area, and the breadth of that mismatch becomes part of the scientific story for that reason. The first region to understand is not a city, a state, or even a single weather office domain. It is the continent-wide shape of the event. The United States is experiencing a moment in which upper air structure, surface heating, regional dryness, and cross-country contrast all lock into one coherent pattern. The heat is real, but so is the geometry behind it. The dryness is real, but so is the circulation that organizes it. The event begins, in its clearest form, as a map-scale atmospheric design extending across the nation, with every local consequence nested inside that larger and steadily holding frame. The next layer of the event is time, and time in weather is never only about the date on a calendar. It is also about the expected state of the land, the angle of the sun, the amount of stored winter cold still lingering in soil and air, and the ordinary pace at which a continent shifts from one season into another. In late March, the United States is not supposed to behave as though summer has already taken hold across major interior regions. Spring at this stage usually carries instability, but it is an instability of transition. Cold air still has influence. The ground has not yet spent many weeks absorbing strong sunlight. The seasonal engine is beginning to turn, but it has not yet reached its full strength. This is what makes timing scientifically important. An extreme event does not mean the same thing in every month. A temperature that might be notable but less astonishing in high summer can become deeply unusual when it arrives at the opening of astronomical spring. The atmosphere is not only producing heat, it is producing heat out of season, before several natural ceilings have normally been removed. One of those ceilings is the seasonal position of the sun. By late March, day length has increased from winter, but solar energy at the surface is still weaker than it becomes in June or July. The sun stands lower in the sky. Its rays reach the ground at a less direct angle than they do in summer. That change in angle affects how much energy each area of land receives over the course of a day. Summer sunlight is more concentrated. Early spring sunlight is gentler, even on clear days. In most years, that geometry alone limits how high temperatures can climb across broad regions. Another ceiling comes from the land itself. During winter, soil and vegetation often retain moisture and cold memory. Cold memory is not a formal technical term, but it helps describe a real process. Land that has recently spent months under weaker sun and cooler air does not warm instantly. It takes time for the surface to accumulate enough heat for sustained summer-like behavior. Moist ground also uses part of the available solar energy for evaporation. When water changes from liquid to vapor, it absorbs energy. That energy does not go into raising temperature directly. In spring, this process often slows the rise of afternoon heat, especially in regions where winter and early spring precipitation have not yet disappeared from the ground. If extreme warmth still develops despite those seasonal limits, then the atmosphere must be arranged in a way that overpowers them. This is why meteorologists pay close attention not just to the warmth itself, but to the seasonal context in which it appears. A record in late March is not simply a number that exceeds older numbers. It is an event that arrives before the background conditions that usually support such heat have matured. The same reading can carry a different physical meaning depending on when it appears in the year. In the heart of summer, very high temperatures are still dangerous, but the surrounding system is at least operating near its expected seasonal maximum. In early spring, the atmosphere is acting ahead of schedule. It is drawing on a level of strength that the season has not fully prepared for. That is why phrases such as early or premature heat matter. They are not casual language. They describe a mismatch between the atmospheric state and the point the seasonal cycle has actually reached. Spring is usually a season of negotiation between lingering winter structure and growing summer influence. Air masses compete. Fronts pass more often. Sharp swings can happen, but they're usually temporary and often followed by cooling. An early season heat event becomes more concerning when it does not appear as a single brief spike, but as part of a broader pattern that holds. Persistence changes the seasonal meaning. One unusually warm day in March can happen under clear skies and downslope winds. Several days of unusual warmth, spread across large areas under a stable upper air regime, indicate that the seasonal transition is being dominated rather than merely nudged. The calendar says spring, but the atmospheric behavior begins to resemble something later and stronger. Timing also matters because living systems are sensitive to it. Plants respond not only to temperature, but to the sequence of temperature through the year. Early warmth can push vegetation toward growth before the season is stable. Once growth begins, later cold can cause damage, and early drying can leave grasses and other fuels exposed at a vulnerable stage. Human systems are also tuned to season. Buildings, utilities, agriculture, and public health planning all assume a general progression of conditions. When strong heat arrives far ahead of normal expectation, adaptation lags behind reality. Cooling habits may not yet be in place. Fire risk may intensify before landscapes or agencies are fully oriented toward warm season operations. Timing, then, is not decorative detail. It is part of the hazard itself. The seasonal frame also influences interpretation of extremes in statistics. A rare event in summer may still sit within a season when high values are more common. The same percentile ranking in March stands against a cooler baseline and therefore signals a larger departure from what the atmosphere usually permits at that point in the annual cycle. The event does not merely cross a threshold, it crosses it early, before ordinary seasonal reinforcement has reached full strength. That early crossing is what gives the pattern part of its scientific gravity. The atmosphere is showing that under the right arrangement of pressure, dryness, and sunlight, the usual spring restraints can be overwhelmed. The date becomes evidence. It tells meteorologists that the event is not only intense but mistimed in a physically significant way. In that sense, the opening of spring is not a backdrop to the story. It is one of the clearest reasons the story matters. The country is not yet standing in the long, fully heated stretch of summer. It is standing near the threshold of spring, when the land and sky would normally still be in measured transition. Yet the atmosphere has accelerated beyond that measured pace and imposed a warm season intensity on a time of year that usually still carries limits. The scientific weight of the event begins there, in the uneasy gap between what the season usually allows and what the atmosphere is now able to produce. Once the seasonal context is understood, the next layer is the temperature field itself, the broad spread of warmth across the landscape, and the way that warmth begins to challenge what has been observed before in the month of March. Temperature anomalies are not simply high readings, they are departures from a baseline, and that baseline is built from long-term averages for a specific place and time of year. A city can be warm in an absolute sense and still not be especially unusual if that warmth falls close to what the calendar normally allows. An anomaly becomes significant when the observed temperature rises well above the local expectation for that date. In this event, that significance appears across multiple regions at once. The readings do not stay confined to one valley, one sheltered basin, or one isolated station. They spread across the American West and parts of the central interior, giving the event geographic breadth and helping distinguish it from ordinary local heat. The first scientific point is that the atmosphere is not merely pushing a few places into comfortingly warm spring afternoons. It is lifting a wide region into temperature ranges that belong more naturally to much later in the year. In some locations, daily highs resemble what would normally be expected in early summer rather than early spring. That comparison matters because people often hear a number without hearing its seasonal meaning. A temperature can sound familiar in isolation. It may not sound alarming until it is placed beside the date. An afternoon in the middle of the 80s in a place that often experiences summer heat can seem ordinary until it is recognized as a March value rather than a June one. The anomaly lives in that mismatch between date and reading. Across this event, the mismatch becomes repeated rather than singular, which is why it deserves close attention. One useful way to picture the anomaly is to think of the continent as carrying its own internal climate calendar. Each place has an expected progression through the year. Winter recedes, spring advances in uneven steps, summer eventually settles in. During this event, several places appear to have jumped ahead in that calendar. The atmosphere is not moving smoothly through the seasonal sequence, it is skipping forward. That jump becomes even more important when it happens over dry inland terrain, where the lack of moisture allows more of the available solar energy to go directly into heating the surface. Dry ground warms quickly. Clear skies reinforce that warming. A stable ridge keeps cooler marine air or frontal relief from interrupting it. Under those conditions, temperatures can surge well beyond the local norm for the date, and once that surge spreads across neighbouring regions, the event begins to look less like scattered record setting and more like a shared continental signal. Record language requires care. Not every station experiencing very high warmth will necessarily set an all-time March record. Some will approach records. Some will break daily records for a specific date. Some will rank among the warmest March days ever observed at that location without reaching the absolute top value. But even where a formal record is not broken, the clustering of unusual warmth itself is meaningful. A map filled with readings near the upper edge of the local historical range shows that the atmosphere is pushing many places toward their statistical limit at the same time. That pattern tells meteorologists more than a single standout number can tell. It reveals coherence. It shows that the event is systematic, not accidental. In the southwest, some inland areas move into triple-digit heat, which in March carries special weight because of the seasonal limits discussed earlier. Farther east across the plains, the temperatures may not always reach the same absolute values, yet they can still be extremely anomalous for the date, especially when combined with very low humidity and strong winds. This is one reason absolute heat and impactful heat are not always identical. A place in the desert can post a higher number, but a place farther north or east can experience a more unusual departure from seasonal expectation, and that departure may contribute powerfully to fire danger, agricultural stress, or public risk. Temperature anomalies also matter vertically as well as horizontally. The surface readings are the values people feel, but those values are connected to a deeper warm structure in the air column above. When a large region warms together, it suggests that the surface is not responding to a tiny local trigger. It is responding to a broader atmosphere that has already shifted into an unusually warm state. This helps explain why the event can encompass city after city rather than staying trapped in a single urban heat island. Urban areas may intensify the warmth locally, but the map-scale anomaly begins before the city adds its effect. The city sits inside a broader warm envelope. Another important aspect is duration. A strong anomaly on one afternoon may reflect a brief burst of downslope wind or a momentary clearing of clouds. Several consecutive days of strong anomalies indicate that the heat is not being erased overnight by ordinary cooling processes. The warm air mass remains in place. The land continues to absorb energy. Minimum temperatures often stay elevated, allowing each following day to begin from a warmer starting point. As that process continues, the anomaly stops being just a peak and becomes an accumulation. The landscape, infrastructure, and living systems all begin responding not just to one high reading but to repeated exposure. This is when the temperature field becomes more than a statistical curiosity. It becomes an evolving physical burden. Scientists also examine how unusual the spread is between regions. During amplified patterns, one part of the country may be far above normal, while another remains closer to or below average. That contrast sharpens the anomaly by reminding observers that the warmth is not coming from a uniform seasonal rise. It is being delivered selectively by the structure of the circulation. The event, therefore, cannot be dismissed as spring simply arriving a little early everywhere. It is a patterned displacement of heat into certain regions with unusual intensity. In that sense, the temperature anomalies are a surface expression of the larger design already described. The readings are the visible result of the circulation. They mark where the atmosphere has chosen to concentrate its warm phase. When many of those readings begin to challenge daily records, monthly records, or long-standing local expectations for late March, the message becomes clearer. The event is not merely warm, it is anomalously, regionally, and persistently warm across a broad part of the nation, and that temperature field forms one of the clearest measurable signs that the atmosphere has entered an exceptional state. After the temperature field becomes clear, attention turns to the forecast itself, because extreme weather is never judged only by what happens in the sky. It is also judged by how well the atmosphere was anticipated. Modern weather prediction is one of the most sophisticated scientific systems in regular public use. Forecast models combine observations from satellites, weather balloons, surface stations, aircraft, ships, radar, and many other instruments. Those observations are fed into mathematical systems that simulate the movement of air, heat, moisture, clouds, and pressure through time. In ordinary short-range situations, these models perform remarkably well. They do not predict every gust or every local pocket of cloud, but over 1 to 3 days they're usually accurate enough that the public treats them as routine. That routine accuracy creates trust, and rightly so. It also means that when a forecast repeatedly underestimates an event over multiple days and across a broad region, the mismatch becomes scientifically important. In this event, the issue is not that one station misses its high by a degree on an odd afternoon. Small misses happen all the time and are part of the normal texture of forecasting. The important feature here is pattern. Observed temperatures in several places come in higher than forecast values, and that tendency repeats. A repeated underforecast is different from noise. Noise is scattered and directionless. One place runs a little warm, another a little cool, and the average error balances out. A systematic error moves in one direction. The atmosphere keeps doing a little more than expected, and because it keeps doing more rather than less, forecasters begin to ask whether the model framework is missing some part of the physical setup. This is why a modest difference in degrees can matter. To the public, a forecast high of the lower 80s followed by an observed value in the middle 80s may not feel dramatic. But for scientists, a persistent gap is a clue. It suggests that the model is seeing the event, but not fully capturing its intensity. The question then becomes why. Forecast models do not simply guess. They approximate the atmosphere using physical laws and simplified descriptions of processes that are too small or too complex to represent in full detail. Those simplified descriptions are called parameterizations: cloud formation, radiation exchange, turbulent mixing near the surface, the influence of soil moisture, and the interaction between terrain and airflow are all represented this way. In most situations, the approximations work very well because they are calibrated against large amounts of historical data and tested against many real events. But when the atmosphere moves toward the edge of its historical range, the approximations can begin to strain. An event can still be forecast in broad outline while being understated in amplitude. This matters especially during strong ridging events, because several warming mechanisms can align at once. Clear skies increase incoming solar radiation at the surface. Dry soil reduces evaporative cooling. Descending air warms through compression. Strong daytime mixing can bring unusually warm and dry air from above down toward the ground. Local terrain can intensify the result further. If any one of those effects is slightly underrepresented in a model, the surface temperature may come in a little low. If several are underrepresented at the same time, the error can repeat across days. Forecast performance is also shaped by model resolution. Resolution refers to how finely the atmosphere and land surface are divided in the simulation. Finer resolution can capture valleys, slopes, coastlines, and urban influences in greater detail, but it also requires more computing power. Some local heating effects occur at scales smaller than what broader forecast systems can resolve cleanly. Downslope warming near mountain fronts, heat pooling in enclosed basins, and sharp moisture contrasts between adjacent landscapes may therefore be softened in the forecast. The model sees the general warmth, but its grid averages the surface more smoothly than the real land does. When the event is already extreme, that smoothing can matter. A forecast that slightly blurs the physical sharpness of the land can slightly blur the final intensity of the heat. There is also the issue of initial conditions. Every forecast begins with an estimate of the present atmosphere, and no estimate is perfect. Small uncertainties in the starting state can grow with time. In a highly amplified and persistent pattern, those small uncertainties may express themselves in the placement or strength of the ridge, the depth of mixing, or the exact dryness of the lower atmosphere. even if the large-scale pattern is correct. A subtle underestimate of dryness or upper-level warmth can tilt the final temperature downward. The repeated nature of the underforecast suggests that this is not merely a single bad initialization. It points more toward a structural tendency during this kind of event. This is why meteorologists sometimes speak of models lagging reality in extreme heat setups. The phrase does not mean forecasting science has failed. It means the real atmosphere is pressing against the upper edge of what the forecast system is accustomed to representing in practice. Forecasters often compensate for this by leaning away from raw model output when observational trends show that the models are running cool. Human forecasters do not simply accept one computer value. They compare models, examine satellite imagery, review upper air soundings, analyze soil moisture, study previous similar cases, and look for persistence in observed error. Operational forecasting is therefore a dialogue between data, physical understanding, and model guidance. When the atmosphere repeatedly exceeds the guidance, that dialogue becomes more cautious. The forecast may still be useful, but it is no longer taken at face value. It is adjusted with awareness that the pattern is overperforming. The deeper scientific issue is that forecast error can itself become part of the event. If a major heat episode is systematically underestimated, then public preparation, risk messaging, and fire weather interpretation may all begin from values that are slightly too low. A small underforecast in temperature can matter greatly when humidity is already collapsing and winds are already strong, because fire danger responds to combinations rather than isolated numbers. Forecast bias, in that sense, is not just a technical footnote. It becomes part of the chain through which the atmosphere meets the human system. What makes this event notable is that the forecast shortfall appears not as a random stumble, but as a coherent tendency within an already exceptional pattern. The models are still seeing the event. They are simply not fully matching the intensity that the real atmosphere keeps delivering, and that repeated gap raises an important scientific possibility the atmosphere may be operating near or beyond the familiar edge of the conditions on which forecast performance has long depended. Above the surface, beyond the thermometers mounted in sun shelters and the dry grasses bending in the wind, the structure of the event becomes clearer in the middle layers of the atmosphere. Meteorologists often look upward, because the air aloft provides a kind of blueprint for what will happen below. Surface heat can feel immediate and local, but it is often being directed by a larger pattern several kilometers overhead. In this event, one of the most important features is a strong ridge in the mid-level atmosphere, especially near the pressure surface known as 500 millibars. A pressure surface is not a fixed height like the top floor of a building. It rises and falls depending on the temperature and density of the air beneath it. Warmer air expands, so the height at which pressure drops to a given value becomes greater. Colder air contracts, so that same pressure level sits lower. When meteorologists say that heights are rising at 500 millibars, they mean the air column below is warm and expanded. That rise is not just a number on a chart. It is a signal that the atmosphere is physically inflated by heat and energy over a broad area. A ridge forms when those heights arch upward over a region, creating a zone of higher pressure aloft and a large-scale pattern that tends to support sinking air. Sinking air matters because descending motion changes both temperature and cloud behavior. As air sinks into denser layers of the atmosphere, it is compressed. Compression warms the air even without adding external heat. This is a basic thermodynamic process. The temperature rises because the air parcel is being squeezed into a smaller volume. At the same time, sinking air suppresses widespread cloud formation. Clouds often develop where air rises, cools, and reaches saturation. In a ridge, the opposite tendency dominates. Air descends, dries, and resists the vertical growth that would otherwise create thicker cloud cover. With fewer clouds, more solar radiation reaches the ground through the day. That additional sunlight warms the land, and the land then warms the air in contact with it. The ridge therefore acts both directly and indirectly. It warms aloft through the expanded air column, and it favours surface warming by maintaining clear, stable conditions below, in strong warm season patterns. This process is sometimes described informally as a heat dome. The phrase is not a separate scientific mechanism so much as a vivid way of describing a persistent ridge that traps and reinforces heat. The word dome can be misleading if taken too literally, because the atmosphere is not enclosed like a lid on a container, yet the image helps convey an important truth. Beneath a strong ridge, the air mass becomes difficult to displace. Cooler intrusions are deflected or weakened. The same region continues receiving sun, sinking air, and limited cloud cover day after day. The ridge is not merely present overhead, it is organising the persistence of the event. Mid-level structure also helps explain why the heat spreads across many landscapes rather than remaining isolated to one surface type. A city can become warmer than nearby countryside because of pavement and buildings, and a desert basin can become warmer than a coastal plain because of dryness and terrain. But those local effects occur inside the broader envelope created by the ridge. The expanded warm air column and the large-scale sinking motion are regional in scope. They create the background environment in which local amplifiers can then operate. In that sense, the ridge does not determine every exact temperature, but it sets the stage on which those temperatures become possible. Another important role of the ridge is its effect on atmospheric stability. Stability describes how willing the atmosphere is to let air parcels rise and mix vertically. Under a warm ridge aloft, the middle atmosphere can become relatively resistant to upward motion, especially when compared with more unsettled patterns that support storms or broad cloud fields. That resistance reduces the chance of the kind of convective cloud development that might otherwise interrupt heating through the afternoon. The sky remains clearer, the sun keeps working. Surface temperatures rise longer and more efficiently. Stability, however, does not mean the atmosphere is inactive. It means the activity is organised differently. The air near the ground can still mix strongly during the day, drawing very dry air downward from above and sharpening low humidity at the surface. So the same ridge that suppresses deep cloud growth can also help create harsher fire weather conditions by fostering strong daytime drying below. The 500 millibar pattern is especially useful because it links directly to the larger steering flow. When meteorologists map these heights, they are not only identifying where the warm air is concentrated, they are also identifying the shape of the broader wave pattern moving, or in this case partly failing to move, across the continent. A pronounced northward bulge in the height field signals that warm air and high pressure are extending far poleward. That bulge is part of the amplified pattern already described on the continental scale. It is one of the clearest fingerprints of the event. The atmosphere is not simply warmer near the ground, it is warmer and more inflated through a deep vertical layer. This vertical depth matters because shallow warmth can be erased more easily by a passing front or by nighttime cooling. Deep warmth supported through the column is more durable, it has structure, it resists quick removal. That durability is one reason the surface heat can feel so relentless once the pattern settles in. The upper air ridge also provides a scientific bridge between observation and rarity. Surface temperatures can vary greatly from place to place, but mid-level heights reveal the underlying state of the broader atmosphere. When those heights climb to unusual values for the time of year, they show that the event is not merely a local accident of sunshine and wind. It is rooted in an anomalous atmospheric architecture overhead. The land is heating because the sky above it has taken on a strong and unusual shape. In this way, the ridge is not a background detail. It is one of the central physical structures of the event. It expands the air column, favours subsidence, suppresses widespread cloud formation, strengthens solar heating at the surface, and helps hold the warm pattern in place. The extraordinary warmth measured below begins here, in the elevated and swollen middle atmosphere, where the event first becomes legible as a coherent physical form. Once the upper air ridge is established, the event can be measured not only as warm but as statistically rare, and this is where the language of percentiles becomes useful. A percentile is a way of locating one value inside the full range of past values. If a reading sits at the 50th percentile, it is near the middle of what has been observed before. If it reaches the 90th percentile, it is already above most previous cases. When conditions climb into the 99th percentile, the atmosphere is no longer operating near the upper side of normal. It is operating near the far edge of the known distribution. This is important because meteorology is not only the study of what air is doing, it is also the study of how unusual that behaviour is relative to a long background record. A hot day can be physically significant, but a hot day in the 99th percentile carries an additional meaning. It means the event belongs to a class that happens rarely enough to deserve special scrutiny. Percentile language can seem abstract at first, but its logic is simple. Imagine a very large archive of earlier March patterns, each one representing what the atmosphere has done during that time of year across many decades. Most cases fall in a broad centre. Fewer cases reach the high end. Only a very small fraction approach the extreme top. If the present event occupies that top band, then the atmosphere is behaving in a way that only a small number of historical counterparts can match. This does not mean the event is impossible or outside the laws of physics. It means it is near the upper tail of the observed climate range for that calendar period. In science, rarity does not make an event mysterious by itself, but it does increase its importance. Rare events test infrastructure, ecosystems, forecasting systems, and long-held assumptions about seasonal limits. In this case, the percentile framing becomes even more striking because it is not being applied to a midsummer pattern. It is being applied to a pattern appearing near the beginning of astronomical spring. A 99th percentile state in late March is not just uncommon in a general sense. It is uncommon against a baseline that is itself much cooler than the summer baseline. This is why the event feels so out of place. The statistical comparison is being made to other late March atmospheres, not to the hottest days of the year. The air is being judged against what March normally allows, and it is rising toward the edge of that March envelope. Meteorologists have several ways to express this kind of extremity. One of them is to compare observed or forecast conditions with a climatological distribution built from long-term records. Another is to use specialized tools developed to show how anomalous a forecast is relative to what is typical for that region and season. These tools matter because raw temperature alone does not always show the full magnitude of the anomaly. A value may look modest in one desert area if judged only in absolute terms, yet when placed against a local March history it may prove exceptionally rare. Statistical tools restore the seasonal and regional context that raw numbers can hide. They tell forecasters not just that it is hot, but that it is hot in a way that lies close to the outer boundary of past experience. One especially useful concept in extreme event forecasting is the idea that rarity can be multi-layered. An event may be extreme in one variable, such as temperature, but less unusual in another. In this case, however, the signal appears across several related fields. Temperatures are high, mid-level heights are high, dryness is pronounced in certain regions, persistence is notable. When several extreme indicators align, confidence grows that the event is not a statistical accident confined to one measurement. It is an integrated extreme. The atmosphere is occupying a rare state across more than one dimension at once. That combination is part of what gives the event its weight. It is not merely one number reaching an odd level. It is a suite of atmospheric characteristics clustering near their upper edge together. The far tail of a distribution also raises a subtle but important question about model performance. Forecast systems are generally built and tested on long records in which ordinary and moderately unusual conditions appear much more often than truly extreme ones. That means the farther an event moves into the tail, the fewer historical examples exist to anchor intuition and calibration. The atmosphere is still following physical law, but the scientific systems used to describe, compare, and anticipate, it may be working with a smaller set of analogues. This helps explain why percentile language often appears alongside caution. When a pattern approaches the 99th percentile, forecasters recognize that they are dealing with conditions near the margin of familiar experience. They begin paying attention not only to the expected value, but also to the possibility that the atmosphere may slightly overperform relative to ordinary guidance. Another reason percentile framing matters is that it communicates scale without requiring a single record to be broken everywhere. A rare event can cover a huge area, even if only some stations set formal records. If many locations occupy the uppermost slice of their historical range at the same time, then the regional pattern itself is extreme. Statistics reveal that shared structure. They show that the event is not a handful of isolated local outliers sprinkled across a normal map. It is a map in which a large cluster of values is shifted toward the upper tail together. In this event, that shared shift is central. The atmosphere is not simply warm in a common way. It is pressing into a rare category over a broad domain, and at a season when such intensity is especially difficult to explain away as ordinary variability. The value of percentile language, then, is not decorative precision. It gives form to the rarity. It tells the difference between an event that is memorable and one that is structurally exceptional. Here the atmosphere is being described in terms that place it near the top of the historical range, and that placement matters because it helps explain why forecasters, emergency planners, and atmospheric scientists all respond with unusual attention. The event has crossed from simple warmth into a statistical tier that marks it as genuinely uncommon, broad in reach, and significant enough to test the boundaries of what late March has usually been able to produce. Behind the surface heat and the swollen ridge overhead lies the larger current that organizes weather across the middle latitudes. The jet stream. It is often described as a fast river of air high in the atmosphere, and that image is useful because the jet stream does more than move quickly. It guides weather systems, separates broad air masses, and helps determine where warmth advances and where cooler air is allowed to settle. Under ordinary conditions, it flows from west to east in a path that undulates but still carries patterns steadily onward. Those undulations are part of normal atmospheric motion. The jet stream is never a perfectly straight line. Yet there is a meaningful difference between a flow that bends modestly while continuing to progress and a flow that becomes strongly amplified, with deep northward bulges and deep southward dips. In this event, that difference becomes central. The jet stream has entered an amplified configuration, and the amplification explains why opposite weather regimes can coexist across the continent at the same time. An amplified pattern means the wave shape of the upper airflow grows larger in its north to south swings, where the flow arches northward, warmer air is drawn poleward, and a ridge often strengthens beneath it. Where the flow dives southward, colder air can spill equatorward and unsettled conditions may develop. This is not a minor adjustment to the map. It is a reorganization of the atmosphere on a continental scale. The country no longer sits beneath a relatively even conveyor of changing systems. It sits beneath a wave pattern whose bends are strong enough to lock very different air masses into neighboring regions. That is why one section of the nation can experience heat, dryness, and clear skies, while another faces cooler, wetter, or more storm-prone conditions. The differences are not random. They are the surface translation of the jet stream's geometry. The jet stream matters because it marks a zone of strong horizontal temperature contrast in the atmosphere. Warm air lies broadly on one side, colder air on the other, and the strength of that contrast helps maintain the flow. The current itself is shaped by pressure differences that arise from uneven heating across the planet. In simplified terms, stronger contrasts favour a stronger, more focused stream, while weaker contrast can support a slower and more meandering one. Whatever the deeper causes in a given event, the immediate result here is clear. The flow aloft is not carrying conditions across the continent in a gentle, quickly changing sequence. It is curving sharply enough to allow one branch of the pattern to intensify warmth over the west and central interior, while another branch supports different outcomes elsewhere. This is why the event cannot be understood as a mere local heat wave. The jet stream has arranged the continent into contrasting atmospheric zones. Another important feature of an amplified jet stream is that it increases the physical distance over which warm and cold air are exchanged. Air from lower latitudes can be drawn far north under a ridge, while air from higher latitudes can plunge far south under a trough. These long excursions sharpen gradients across the map. A gradient is simply a difference over distance, but in meteorology gradients matter enormously because they reveal where the atmosphere is stretched and where energy contrasts are strongest. In this event, the large temperature contrast across the country is part of the signal that the jet stream is deeply contorted. The atmosphere is not easing into spring with mild regional variation. It is dividing itself into pronounced sectors whose boundaries reflect the distorted path of the high-altitude flow. The jet stream also controls the track of storm systems. When its path shifts, storms are diverted. Regions under the ridge may be cut off from the ordinary passage of fronts or cloud-bearing systems that would otherwise temper the heat. Regions closer to the trough or downstream disturbances may receive the opposite result, with more clouds, precipitation, or colder intrusions. This redistribution of storms reinforces the pattern already in place. The warm region remains warm partly because the usual mechanisms that break or interrupt heat are displaced. The cooler or wetter region remains under those conditions because the same steering flow keeps sending disturbances along that route. In this way, the jet stream does not merely create contrast once, it helps maintain it by controlling what kinds of weather are allowed to enter each region over time. Amplification also has a visual clarity on upper air maps that forecasters recognize quickly. Instead of a smoother band moving across the continent, the height contours bend into large arcs. Those arcs correspond to ridges and troughs, and their exaggerated form signals a pattern with greater potential for persistence and regional extremes. The sharper the bend, the more the flow begins to favour prolonged occupation of certain air masses over certain places. This is one reason the jet stream is so central to the story. It provides the mechanical explanation for the arrangement already visible on the surface. Without it, the map of heat, dryness, and contrast would seem disconnected. With it, the pattern becomes intelligible. The broad warm sector, the drying plains, and the diversion of more unsettled conditions elsewhere all become expressions of one atmospheric current taking on a strongly amplified shape. The scientific value of this perspective is that it shifts attention away from isolated symptoms and back towards structure. Heat is one symptom, low humidity is another, fire risk is another still. But the jet stream is the organizing flow that helps place those symptoms where they appear. It is the high-altitude architecture through which the atmosphere sorts its different regimes across the continent. In this event, that architecture has become unusually curved, and the curvature matters because it sets up the very possibility of simultaneous extremes. The event therefore deepens from a story about unusual temperatures into a story about atmospheric arrangement. A river of air high above the country is bent into a pattern strong enough to separate and sustain sharply different realities below. The warmth in the west and interior is not floating free. It is riding beneath a northward swell in the flow. The other regional conditions are not background noise. They are the other side of the same wave. This is how the jet stream enters the narrative, not as a technical detail added for completeness, but as the large moving boundary that has reshaped the national weather map and made the event physically coherent from one end of the country to the other. Amplification alone does not fully explain the severity of the event. A strongly bent jet stream can still move weather along if the wave pattern continues progressing from west to east at a healthy pace. What gives this event more of its weight is that the pattern does not simply bend, it slows, stalls, and begins to hold its shape over the same geography for longer than an ordinary warm spell would. This is where the idea of blocking becomes central. A blocking pattern is a configuration in which high pressure resists the normal downstream movement of weather systems and acts almost like an obstacle in the flow. It does not create a wall in a literal sense, but it alters the path of surrounding air so that systems are diverted around it rather than passing cleanly through. The result is persistence. The same broad region remains beneath similar atmospheric conditions day after day, and persistence is what transforms unusual weather into accumulating risk. Under ordinary spring conditions, warmth may build for a day or two and then weaken as a front arrives. Clouds increase, or a new disturbance changes the air mass. That natural turnover is one of the reasons many moderate heat episodes end before they produce deeper consequences. Blocking interrupts that turnover. The atmosphere stops behaving like a steady stream of passing systems and starts behaving more like a pattern locked in place. For the region under the ridge, this means repeated sunshine, repeated sinking air, repeated dryness, and repeated heating of the land surface. Each afternoon adds to what the previous afternoon has already done. Each night begins from a warmer starting point than a normal night would. The pattern becomes cumulative, not just momentary. This is why duration matters so much in atmospheric hazards. A single hot day can be unpleasant. Several hot days under a stalled regime can begin to change fuels, soils, infrastructure loads, and physiological stress. Blocking gives the event time to deepen. It is not that the atmosphere produces one dramatic surge and then ends the story. It keeps feeding the same region with the same broad conditions until the consequences become harder to reverse. The land surface responds to that repetition. Soil loses moisture. Vegetation dries further. Urban materials store and release heat over multiple cycles. Forecast errors become more meaningful when the same bias repeats under the same slow-moving setup. Even systems that are designed to recover overnight begin losing that recovery window when warm air remains overhead and the pattern refuses to rotate out. In this event, the stalled nature of the ridge is especially important because the most dangerous outcomes are not tied to heat alone. Fire weather depends on the convergence of warmth, low humidity, wind, and dry fuel. Blocking gives those ingredients time to align more fully. A brief episode of hot dry wind may raise concern, but a blocked regime can lower fuel moisture day after day, making each successive afternoon more responsive to ignition. The atmosphere is no longer offering interruption. It is reinforcing the same drying logic over a broad region, and that reinforcement is part of what elevates the event from unusual to hazardous. From a fluid dynamics perspective, blocking is one of the ways the atmosphere expresses nonlinearity on large scales. Nonlinearity means that small changes in flow can produce disproportionately large differences in outcome. A slightly different placement of the ridge or a slight slowdown in the jet stream can mean the difference between a passing warm spell and a multi-day lock of extreme conditions. Blocking is not a rare invention of the present era. It has long been part of the known behavior of the atmosphere. Scientists have documented blocked patterns for decades in many parts of the world. What makes any specific event noteworthy is how persistent the block becomes, how strong the ridge beneath it grows, and what surface consequences accumulate while it remains in place. In this case, the consequences are broad enough that the stall itself becomes a central scientific fact. The event is intense partly because it is lingering. That lingering has a geometric component. Once a ridge becomes established and the surrounding flow bends around it, the pattern can begin reinforcing its own position. Clear skies beneath the ridge favour continued warming of the underlying air mass. The warm expanded column helps maintain higher heights aloft. Systems that might otherwise break the pattern are deflected northward or southward. The ridge does not merely remain by chance. It can be supported by the larger shape of the flow that has already developed around it. This is why blocking often feels stubborn to forecasters and to the public alike. The usual expectation that tomorrow will shift towards something different becomes weaker. The atmosphere remains committed to the same arrangement. Persistence also complicates interpretation, because a stalled pattern can make each local reading seem repetitive, when in fact the scientific significance is growing. Another hot day may look similar on a chart to the previous one, but the cumulative effect on land and fuel is not the same. Drying after 3 days is not equal to drying after 1. Overnight warmth after several days of heat is not equivalent to overnight warmth at the start of the event. The blocked pattern turns repetition into escalation. This is one reason meteorologists often become more concerned as a stagnant setup continues, even if the daily numbers stop increasing dramatically. The atmosphere does not need to become hotter every day to become more dangerous overall. It only needs to remain extreme long enough for consequences to compound. In the broad structure of the event, blocking therefore acts as the timekeeper. The ridge supplies the warm architecture, the jet stream amplification supplies the continental contrast. Blocking supplies the persistence that allows the structure to matter more with each passing day. Without persistence, the event would still be notable, but many of its deeper consequences would be muted. With persistence, the event begins reshaping conditions at the surface in ways that prepare the ground for the next layer of the story. Heat settles into the southwest not as a passing spike, but as a prolonged occupation. The land has time to respond, and the statistics of rarity start translating into lived physical change. The atmosphere, by refusing to move on its ordinary schedule, turns extreme weather into an extended state, and that extended state is what gives the event much of its unusual seriousness. Within the larger blocked pattern, the southwest emerges as the region where the heat becomes easiest to see in its most concentrated form. This part of the country is already familiar with high temperatures, but familiarity can be misleading. A desert or inland basin is not automatically in an extreme state simply because it becomes hot. The scientific question is not whether the southwest can produce large numbers on a thermometer. It is whether those numbers are arriving at a time of year and in a regional pattern that places them outside the normal seasonal envelope. In this event, the answer is yes. The southwest becomes the clearest ground-level expression of the ridge overhead because its landscapes are especially responsive to the combination of clear skies, dry air, and descending motion. Under those conditions, the surface can warm with remarkable efficiency, and once that process begins under a persistent block, the region moves from spring warmth into heat that belongs more naturally to much later in the year. The geography of the southwest helps explain why the response is so intense. Much of the region consists of deserts, dry valleys, inland basins, and elevated plateaus separated by mountain ranges. Dry ground absorbs solar radiation readily, and because there is often limited surface moisture available for evaporation, a large share of the incoming energy goes directly into raising temperature. This is a basic energy balance. If sunlight reaches the surface and little water is present to consume that energy through evaporation, the land warms faster. That warmed land then heats the air above it. Clear skies beneath the ridge amplify the process by allowing strong daytime solar input without the interruption of widespread cloud cover. The atmosphere aloft is already warm and stable, so the surface heating takes place inside an air mass predisposed toward further warmth rather than resistance. Terrain adds another layer. Air moving down from higher elevations into valleys and basins is compressed as it descends, and compression warms it. This process can sharpen already high temperatures along the eastern sides of mountain ranges and in enclosed lowlands where the heated air collects. The result is not uniform heat across the entire southwest, but a pattern in which certain interior communities become focal points of exceptional warmth. Inland Southern California, the lower deserts of the region, and basin areas removed from direct marine influence are particularly vulnerable because they combine strong solar heating, dry air, and local topography that favors warming rather than relief. Coastal moderation, where it exists, weakens rapidly with distance inland and with mountain barriers that prevent the easy movement of cooler air. This is why a suburban valley inland from the coast can behave far more like an interior desert than like the nearby ocean front. The southwest also reveals how absolute temperature and seasonal anomaly can work together. A triple-digit value is always physically intense, but in March it carries special weight because the usual spring limits are still in place. The sun angle is lower than it will be in summer. Nights are longer than summer nights. Many of the seasonal feedbacks that help sustain the hottest part of the year are not yet fully developed. If temperatures still rise into the range more often associated with June, July, or August, then the event is not simply hot. It is ahead of schedule by a substantial margin. The calendar becomes part of the diagnosis. A place known for heat is experiencing the wrong kind of heat for the time of year, and that mismatch is one reason the Southwest becomes the visual center of the event. Another reason is that the region makes atmospheric processes legible. In more humid climates, cloud cover, vegetation, and marine air can complicate the surface response to a ridge. In the Southwest, the physical chain from ridge to sunshine to surface heating is often more direct. The land is already dry enough that changes in the overlying air mass are expressed quickly. A strong ridge can therefore produce a rapid and vivid response. Temperatures climb not because the region is inherently dramatic, but because the background dryness allows the atmospheric forcing to convert efficiently into measurable heat. The Southwest acts like a sensitive surface under a strong lamp. When the atmospheric lamp brightens and stays fixed, the signal appears clearly. Persistence is again important here. A single day of extraordinary heat in the region would still be notable, but repeated days under the same broad setup change the nature of the event. Each day begins with residual warmth in the ground and lower atmosphere. Surfaces that absorbed heat yesterday still contain part of it today. Buildings, roadways, bare soil, and rock all participate in this storage and release cycle. The region does not reset fully overnight, especially when the air mass above remains warm and the sky stays mostly clear. That incomplete reset helps explain why subsequent days can remain intense, even without an increase in the large-scale forcing. The pattern does not need to grow much stronger. It only needs to continue. The Southwest therefore becomes more than a passive recipient of the broader circulation. It becomes a place where the circulation's logic is made plain. The ridge aloft suppresses clouds and supports subsidence. Dry air reduces evaporative cooling. The terrain favors local warming in basins and valleys. The stalled pattern prevents relief from arriving quickly. Together, these factors produce surface temperatures that threaten records, stress communities, and signal that the atmosphere is operating at an unusual level for late March. Importantly, this regional heat is not separate from the rest of the national story. It is one branch of the same amplified and blocked pattern that is drying the plains and creating sharp contrast elsewhere. But in the southwest, the physical mechanisms align so cleanly that the heat appears in its most concentrated and unmistakable form. The region becomes ground zero, not because it is the whole event, but because it is where the event's atmospheric design is translated into temperature with the greatest directness. The numbers there show what happens when a rare springtime ridge settles over a landscape already primed to convert light and dryness into heat, and when that settlement lasts long enough for the land itself to start carrying part of the pattern forward from one day to the next. When the strongest daytime heat settles over the southwest, the atmosphere begins influencing another part of the daily cycle that often matters even more for physical stress than night. People often imagine danger in heat as something that peaks in the middle of the afternoon, when the sun is highest and the air feels most intense. That is true in part. But a heat event becomes much more serious when the warmth does not fade sufficiently after sunset. Nighttime cooling is one of the most important recovery mechanisms in both natural and human systems. Buildings release the heat stored through the day. Roads and rooftops gradually lose energy to the sky. Bodies reduce accumulated heat stress when surrounding air becomes cooler. Plants recover some moisture balance. Power demand may ease. When the night stays unusually warm, that recovery window narrows or partly disappears. In this event, the southwest shows how a persistent ridge can transform not only daytime highs, but also the thermal rhythm of the full 24-hour cycle. Warm nights in dry regions can seem counterintuitive, because deserts are often associated with large day-to-night temperature swings. Under ordinary clear and dry conditions, the ground loses heat efficiently after sunset by radiating it upward into the atmosphere and into space. With little moisture and often few clouds, some deserts can cool quickly once the sun goes down. That is one reason a very hot day in a dry climate does not always produce a dangerously warm night. But this relationship changes when the larger air mass itself is unusually warm, and when the surface has spent several consecutive days storing heat. In that case, the night begins from a much hotter starting point. The air descending beneath the ridge remains warm through depth, which reduces the atmosphere's ability to shed the accumulated surface heat rapidly. The surface still radiates energy away, but it is radiating into an environment that is already warm, stable, and not easily refreshed by a cooler incoming air mass. The result is that minimum temperatures remain elevated, sometimes dramatically so for the season. Nighttime warmth is also shaped by land cover and construction. This is where the urban heat island becomes especially important. An urban heat island is not a metaphor. It is a measurable effect in which cities remain warmer than surrounding rural areas, especially after dark, because built materials absorb and store large amounts of solar energy during the day and release that energy more slowly at night. Pavement, brick, concrete, rooftops, walls, and other dense surfaces have different thermal properties than open soil or vegetated land. They do not cool as quickly, and they often reduce airflow through the street environment as well. Trees and open ground can provide shade and evaporative cooling, but in heavily built landscapes those moderating influences are often weaker or less evenly distributed. Under ordinary circumstances, the urban heat island may add a modest amount to nighttime temperature. Under an already extreme heat regime, it can become a critical amplifier. The city does not create the regional event, but it can make the lived nighttime experience materially harsher. In parts of the inland southwest, this process can be especially pronounced because cities are often embedded within basins or valleys already prone to daytime heat buildup. The urban surface stores the sun's energy through a long, bright day. After sunset, that stored heat leaks back into the surrounding air for hours. If winds remain light, or if the air mass overhead remains very warm, the release continues without much dilution. This can hold overnight lows at levels more typical of much later in the year. The significance of that is physiological as much as meteorological. Human bodies rely on cooler nighttime conditions to reduce internal heat burden, when surrounding air remains warm. Especially indoors in buildings that also retain heat, the body struggles to recover. Consecutive hot nights therefore increase cumulative stress even if daytime highs remain the same. Heat risk is not only a matter of how high the maximum temperature climbs, it is also a matter of how low the minimum temperature fails to fall. The night becomes part of the hazard. Elevated nighttime temperatures also affect infrastructure. Air conditioning systems must work longer and more continuously when indoor spaces cannot cool naturally after dark. Electrical demand may remain elevated deep into the night, placing additional stress on energy systems. Roads, rails, and other built surfaces experience longer periods of thermal loading. Homes without efficient cooling or with poor insulation retain heat from one day into the next. For vulnerable populations, the absence of a cool night can turn a difficult heat episode into a dangerous one. These impacts begin with atmospheric conditions, but they are intensified by the built form of the places exposed to them. In that sense, urban heat retention is where meteorology and human design meet most directly. The ridge provides the persistent warmth. The city stores and redistributes it through the night. There is also an ecological side to warm nights. Many plants and animals are adapted not just to average temperature but to daily cycles of heating and cooling. When nights remain unusually warm, respiration, moisture loss, and metabolic stress can all shift. In dry regions already under seasonal strain, the loss of nighttime relief can further reduce the resilience of vegetation. That matters for fire weather as well, because fuels that do not reabsorb much moisture overnight remain more available to burn the following day. The atmospheric event therefore extends its influence across systems that at first glance may seem separate. The same blocked ridge that produces extreme afternoon warmth also helps create nights that do not adequately cool. The same urban surfaces that intensify local heat after sunset also lengthen the time during which people remain exposed in the southwest, where the regional heat is already intense. This daily carryover becomes one of the event's most consequential features. Heat no longer behaves as a sharp spike tied to daylight alone. It becomes a continuous presence, weakening the distinction between day and night and reducing the time available for recovery. That continuity is one reason the event becomes more dangerous than the afternoon thermometer by itself would suggest. The warmth does not simply arrive, peak, and recede. It lingers in streets, walls, air, and bodies, and by the time the next morning begins, the atmosphere has already preserved part of the previous day inside the landscape. East of the hottest desert and basin regions, the event changes character without leaving the same larger atmospheric system. Across the Great Plains and adjacent interior grasslands, the most important story is not always the highest temperature reached on a thermometer. It is the drying of the land and the lower atmosphere together. Dryness can be less visually dramatic than record heat, yet it is often more consequential because it alters how the landscape responds to every spark, every gust of wind, and every additional day beneath the stalled pattern. In the plains, dryness is not simply the absence of rain on one afternoon. It is a cumulative physical state in which humidity falls, fuels lose moisture, soils release what water they still hold, and the air begins behaving more like that above an arid region than that above a living spring grassland. The atmospheric setup behind this change begins with the same ridge and blocking structure already described. Sinking air beneath a ridge tends to dry as it descends. As air is compressed and warmed, its capacity to hold water vapor increases. If new moisture is not added, the relative humidity falls. Relative humidity is a comparison between how much moisture the air actually contains and how much it could hold at that temperature. Warm the air without adding moisture, and the relative humidity drops. This principle helps explain why drying can accelerate rapidly during warm ridge events even before the hottest part of summer arrives. The same sun that heats the ground also encourages evaporation from soil and vegetation. Winds then mix the lower atmosphere and carry moisture away, replacing it with drier air from above or from upwind regions. In the plains, where large open landscapes allow vigorous daytime mixing, this process can be especially efficient. The air mass does not merely feel dry, it actively extracts moisture from the surface through repeated daytime exposure. The land surface is a crucial part of this story. Grasses, crop residue, shrubs, and surface litter all contain water, even when they appear dry to the eye. Their flammability depends strongly on how much of that water remains. During a persistent warm and windy pattern, fine fuels such as grasses can lose moisture very quickly. Fine fuels respond on short timescales because they are thin and exposed. They exchange moisture readily with the surrounding air. When the humidity collapses through the day, those fuels can dry within hours. Coarser fuels respond more slowly, but even they begin trending downward when the pattern lasts for days. This is why persistence matters so much. One dry afternoon can lower fuel moisture temporarily. Several dry afternoons, combined with warm nights and little recovery, can reset the flammability of an entire region. Soil moisture plays a parallel role. Moist soil uses some incoming solar energy to evaporate water, which cools the surface. Dry soil lacks that buffer. More of the sun's energy then goes into raising temperature directly. This creates a feedback. As soil dries, daytime heating becomes more efficient, and as heating becomes more efficient, relative humidity falls further. The surface and the atmosphere start reinforcing one another. In grassland regions, this can shift the landscape from spring-like moderation toward fire-prone behavior very quickly. The plains are particularly sensitive because they cover vast contiguous areas with relatively low barriers to wind. Once the atmosphere above becomes hot and dry, the land below can be conditioned over millions of acres in a similar way. There's no need for a dramatic local trigger. Broad exposure is enough. Another important element is the mismatch between calendar and landscape condition. In many years, spring vegetation and residual cool season moisture help moderate fire risk in parts of the plains before the hottest part of summer arrives. When a blocked warm pattern develops early, it can strip away that moderation before the season is ready. Grass may still be in a transitional state, with portions cured from the cold season and new growth not yet sufficient to raise moisture content across the landscape. In that mixed condition, drying can have outsized consequences. The fuels are present, continuous, and often exposed. The atmosphere then presses down with low humidity and warmth, turning a broad living surface into something much more combustible. Dryness in the lower atmosphere is also physically uncomfortable and biologically stressful. Very low humidity increases evaporation from skin, plants, and soil alike. Water is drawn outward from exposed surfaces with unusual speed. Lips crack, eyes dry. Nasal passages become irritated, and vegetation loses water even when the air temperature alone might not seem catastrophic. In meteorological terms, the low humidity increases the vapor pressure deficit, which is a way of describing the atmosphere's demand for moisture. A high vapor pressure deficit means the air is able to pull more water from the surface. That demand becomes especially severe during warm afternoons with strong mixing. The atmosphere acts like a persistent drying mechanism operating over a huge area. This does not create headlines as readily as a record high in a major city. But from the standpoint of fuel readiness, it can be even more decisive. The plains therefore represent a shift in emphasis from heat as spectacle to dryness as preparation. The land is being conditioned. The atmosphere is doing work on the fuels before any flames appear. This preparation is not abstract. It is measurable in falling humidity, increasing surface curing, and the continued lack of meaningful overnight recovery. Each day under the blocked pattern removes a little more resilience from the landscape. Each warm, dry afternoon leaves grasses closer to immediate ignition. Each night that fails to restore moisture carries the next day forward before the sun has even risen. In this region, the event's seriousness is found less in a single extreme number and more in a regional transformation of surface state. A broad grassland system that should still retain some seasonal buffer is being pushed toward a fire-ready condition by the same atmospheric design that is producing the record warmth farther west. The pattern is still one event, but here its most important effect is not simply making the air hotter. It is making the land easier to burn. Once the plains have dried into a more combustible state, the event enters the stage where fire weather can be understood as a complete system rather than a simple consequence of heat alone. Fire weather depends on several ingredients acting together, and the danger rises most sharply when those ingredients align in the same place at the same time. The essential elements are heat, low humidity, wind, and available fuel. Each one matters on its own, but their interaction matters more than their separate presence. A warm day without wind may not spread flame quickly. Strong wind over moist ground may not produce major fire behavior. Dry grass without a source of ignition may remain only a latent risk. The atmosphere becomes dangerous when it assembles all four conditions at once and then sustains them long enough for the landscape to respond. In this event, that assembly is one of the most important scientific facts. The air is warm enough to lower relative humidity further. The humidity is already low enough to dry vegetation efficiently. The fuels are continuous across large areas of grassland, and the winds are strong enough to convert ignition into rapid spread. Fire weather, in that sense, is not a side story. It is the operational form that the atmospheric pattern takes when it meets the plains landscape. Heat contributes to fire risk in more than one way. It does not ignite fuels by itself under ordinary outdoor conditions, but it accelerates the processes that make fuels easier to ignite. Warm air can hold more moisture than cool air, which means that relative humidity tends to fall as temperature rises unless water vapor is added at the same rate. A lower relative humidity increases the drying power of the atmosphere. Fine grasses and surface litter lose water more quickly, and once their moisture content drops far enough, they require very little additional energy to ignite. Heat also promotes stronger daytime mixing in the lower atmosphere, which can transport even drier air from aloft down toward the surface. That vertical mixing can make the afternoon fire environment much harsher than the morning one. As the sun climbs, the lower atmosphere becomes more turbulent, and the land surface is exposed to air that is not only warm but exceptionally thirsty for moisture. Humidity is the next key ingredient, and in many ways it is the most direct measure of how aggressively the atmosphere can draw water from fuels. Relative humidity near the ground is important because fine fuels exchange moisture with the air rapidly. When humidity falls to very low values, grasses can cure almost in real time through the afternoon. Moisture that might have softened the fuel bed earlier in the day is lost quickly, leaving stems and blades ready to catch from a small ignition source. Low humidity also means that even if temperatures are not at their absolute maximum, the fire environment can still be severe. This is one reason fire weather cannot be judged by temperature alone. A somewhat lower temperature combined with extremely dry air can produce a more volatile landscape than a hotter but more humid day. In this event, the low humidity over the plains is not incidental. It is a product of the same sinking, warming, and mixing processes already set in motion by the ridge and the stalled pattern. Wind is the factor that turns a flammable landscape into a rapidly moving fire environment. Wind supplies oxygen to combustion, bends flames forward into unburned fuel, and pushes fire across the ground with a speed that can outrun expectations. It also carries embers ahead of the main flame front, allowing new ignitions to develop beyond the visible edge of the fire. This process, often called spotting, is one of the main reasons fast-moving grass fires can behave unpredictably and overwhelm suppression efforts. Wind also dries fuels directly by increasing evaporation at the surface. A breezy, dry afternoon does not merely support fire spread after ignition. It helps prepare the fuels before ignition ever occurs. On the plains, where terrain is often open and uninterrupted over long distances, strong winds can maintain that drying and spreading effect across very broad areas. The same openness that defines the landscape as grassland also makes it vulnerable to wind-driven fire behavior. Fuel is the final ingredient, and in this event the fuel is both abundant and continuous. Grasslands are especially prone to rapid fire spread because the fuels are fine, closely spaced, and widespread, unlike forests, where canopy structure and larger woody fuels may govern the rate of spread in different ways. Grass fuels can ignite quickly and carry flame low and fast across the surface. Their continuity matters. A fire does not need large gaps to pause or lose momentum when the land is covered in dry. Connected vegetation. If winter and early spring have left behind cured grasses, and if new growth has not yet created enough moisture-rich green cover to interrupt the fuel bed, then the region becomes highly responsive to even small ignition sources. In such a setting, the landscape does not need to be transformed into something unfamiliar. It only needs to be dried a little further and exposed to wind. The atmosphere does the rest. The interaction of these ingredients is what makes the event particularly dangerous. Fire behavior is not additive in any simple sense. Heat lowers humidity, low humidity dries fuel, wind dries fuel further and increases spread after ignition. Dry fuel allows a small spark to become flame quickly. Flame in wind generates more spotting, which creates more ignition points. Each factor strengthens the others. This is why a fire weather day can escalate suddenly from concern to emergency once the atmosphere crosses certain thresholds. The landscape may appear stable until one ignition occurs, but the underlying system is already primed for rapid reaction. In operational forecasting, this is the difference between a difficult burn environment and an explosive one. The atmosphere has moved beyond inconvenience and into a configuration in which suppression can become difficult almost immediately after a fire starts. Another important part of fire weather is timing through the day. Conditions usually worsen from morning into afternoon as temperatures rise, humidity falls, and mixing intensifies. If the broader pattern is persistent, the morning may also begin from an elevated baseline because overnight recovery has been weak. That means the fire environment starts severe and becomes harsher still by mid-afternoon. The window of dangerous fire behavior widens. Fuels that might once have regained a little moisture overnight now remain receptive much earlier in the day. The atmospheric event is therefore not only assembling the right ingredients, it is stretching the hours during which those ingredients operate together at high intensity. What emerges from all of this is a fire weather system that is fully built from atmospheric structure, surface response, and daily repetition. The heat wave and the fire threat are not parallel stories. They are the same story viewed through different physical outcomes. Over the southwest, the ridge expresses itself most clearly through extreme temperature. Over the plains, the same ridge expresses itself through drying, wind exposure, and fuel readiness. The scientific logic remains unified. A rare and persistent atmospheric pattern has assembled the conditions under which ignition becomes more likely, spread becomes faster, and control becomes harder. Fire weather is therefore the event made operational. It is the point where the abstract language of ridges, blocks, and percentiles turns into the immediate physical reality of a landscape prepared to burn. When the atmosphere reaches a state that is both extreme and operationally dangerous, forecasting language becomes more formal, and those formal statements are one of the clearest ways meteorology enters public life. Warnings, watches, outlooks, and fire weather alerts are not dramatic embellishments placed on top of a weather story. They are the translation layer between atmospheric science and real-world decisions. In this event, that translation is especially important because the risk is broad, persistent, and built from several reinforcing factors rather than one isolated hazard. Emergency agencies do not respond only to heat in the abstract. They respond to the way heat combines with fuel dryness, wind, limited overnight recovery, and the possibility that a single ignition can overwhelm local capacity. This is where operational warnings become more than a technical detail. They show how the atmosphere is being interpreted by the institutions responsible for public safety and fire response. One of the most important alerts in this setting is the red flag warning. A red flag warning is issued when critical fire weather conditions are either occurring or expected soon. The phrase does not mean that a fire is already burning. It means the environment has become supportive enough that if ignition occurs, rapid and potentially difficult fire spread is likely. That distinction matters. A red flag warning is not a report of disaster after the fact. It is a recognition that the atmosphere and the landscape have moved into a state where disaster can begin quickly. It is therefore one of the most operationally consequential products in warm season and shoulder season forecasting. For meteorologists, issuing such a warning means that multiple thresholds involving humidity, wind, and fuel condition are being met or are likely to be met together. For emergency services, it means preparedness needs to rise. For the public, it means ordinary activities may carry unusual risk. Large warning areas also convey information about scale. When a red flag warning covers a small local zone, the hazard may still be serious, but it remains geographically concentrated. When warnings expand across multiple counties, multiple states, or vast stretches of the plains, the meaning changes. It suggests the fire environment is not being driven by one local wind corridor or one unusually dry valley. It is being produced by a regional atmospheric pattern broad enough to challenge many jurisdictions at once. Scale matters operationally because emergency response systems are built with assumptions about mutual aid, resource movement, and the idea that intense demand in one place can be supported by capacity from another. A large-scale warning area weakens that assumption. If many places are under the same severe fire weather conditions simultaneously, then engines, crews, aircraft, and incident support cannot be shared as freely because neighbouring regions may be facing comparable risk at the same time. The atmosphere stretches the response network simply by being large. Persistence compounds this stress. A single dangerous afternoon can be managed differently from several dangerous afternoons in sequence. Crews can stage for one peak day, and public messaging can concentrate around one forecast window. But when the blocked pattern keeps the hazard in place, fatigue becomes a factor. Equipment remains deployed. Agencies must maintain elevated readiness across repeated operational periods. Fine fuels do not recover meaningfully overnight, so each day begins with concern already in place. The warning environment becomes cumulative in the same way the physical event becomes cumulative. Emergency managers are not just responding to one forecast. They are responding to a sequence of forecasts that continue confirming the same general danger. In that setting, even small forecast changes matter. A slight increase in expected wind speed, a slight drop in humidity, or a slight expansion of the warned area can alter staffing decisions and fire attack strategy. Operational implications extend beyond firefighting agencies. Utilities may restrict maintenance work or alter procedures near vulnerable lines. Land managers may suspend prescribed burning. Transportation agencies may monitor visibility risk in smoke-prone corridors or prepare for wind-driven dust in dry zones. Public officials may issue burn bans or reinforce messages about equipment use, outdoor sparks, and evacuation readiness. Hospitals and health systems may prepare for heat-related strain in places where the hot air mass is also affecting people directly. The atmosphere, therefore, does not remain inside the weather office once warnings are issued. It spreads into governance, logistics, public communication, and the management of ordinary daily life. That shift is one of the clearest signs that a weather event has crossed from unusual to societally consequential. Another important operational feature is the relationship between warning language and uncertainty. Forecasting agencies do not wait for absolute certainty before issuing alerts. If they did, warnings would often come too late to be useful. Instead, they assess the probability and severity of the anticipated environment. In a pattern like this, uncertainty often lies less in whether dangerous conditions will exist, and more in exactly where the worst overlap of wind, humidity, and ignition will occur. That means warning maps may cover areas larger than the eventual fire footprint, not because the science is weak, but because the atmosphere is supporting dangerous potential over a broad domain. Operational meteorology must think in terms of consequence, not only exact point verification. If the environment is primed across millions of acres, it is rational to warn broadly, even though only some locations may experience ignition. The warnings also reveal something about trust in observation. When models have been running slightly cool and the atmosphere is repeatedly overperformed, operational forecasters tend to lean more heavily on real-time trends. Surface observations, upper air soundings, satellite imagery, and local fuel reports gain even greater weight. This can make warning decisions more conservative in the best sense of the word. Conservative here does not mean minimizing concern. It means respecting the possibility that the atmosphere may continue exceeding modeled expectations. If the pattern has already shown a tendency to produce higher temperatures or lower humidity than forecast, then emergency messaging must account for that behavior. The gap between modeled risk and realized risk becomes part of the operational judgment. What emerges in this stage of the event is a picture of atmospheric science functioning as public infrastructure. The ridge, the dryness, the wind, and the blocked pattern are physical realities. But warnings are the mechanism by which those realities are converted into action. A red flag warning, a fire weather outlook, or a strongly worded forecast discussion is not just language on a screen. It is a signal to a chain of institutions that the environment has crossed into a state where ordinary assumptions no longer hold. Ignition can spread faster. Response may be stretched. Recovery overnight may be weak. The same broad region may remain vulnerable tomorrow. In this way, operational warnings do more than describe the event. They reveal its practical meaning. They show that the atmosphere is not merely rare in a statistical sense or interesting in a scientific sense. It is consequential enough that emergency systems must reposition themselves around it. At this stage, the event returns to the models, but now from a wider scientific angle. The earlier question is no longer only why a forecast came in a little low on one hot day. The deeper question is whether episodes like this expose limits in how forecasting systems and climatological baselines represent an atmosphere that may be shifting toward more frequent extremes. Weather models are built on physics, but they are also built on approximation, calibration, and historical reference. They solve equations that describe motion, heat, moisture, and pressure, yet they do so using starting conditions, parameter choices, and empirical corrections that have been shaped by many years of observed behavior. That means the model is always a meeting point between timeless physical law and a historically informed description of how the atmosphere usually behaves. Most of the time, that meeting point works extraordinarily well. But an event near the edge of the seasonal distribution raises the possibility that the historical frame itself may be becoming less representative of the most consequential situations. A climate baseline is, in simple terms, the reference period against which present conditions are compared. It helps define what is normal, what is anomalous, and how unusual a forecast pattern may be. Baselines matter in weather as much as in climate because they shape interpretation. A temperature of a certain value means one thing if the reference climate suggests it is moderately above normal, and something more serious if the reference climate shows it belongs near the far upper edge of March experience. Forecast systems also depend on baselines in subtler ways: soil moisture expectations, radiative assumptions, boundary layer behavior, and many forms of statistical post-processing are all influenced by the historical atmosphere used to tune and evaluate the models. If the most extreme ridging events or the driest early season combinations are becoming more common than they once were, then a system calibrated across older and newer conditions together may produce outputs that lean toward the older center of the distribution. In that case, the model does not fail because its equations are wrong. It underestimates because its habitual frame is slightly cooler, slightly moister, or slightly less extreme than the atmosphere is now prepared to deliver. One way to think about this is through the idea of training range. Even outside machine learning, scientific systems perform best in the conditions they encounter most often. Forecast models are constantly tested against ordinary weather and against many kinds of moderate extremes. Truly rare events occur less often, which means there are fewer historical cases from which to refine model behavior at the edge. If the edge itself is shifting, then the problem becomes more complicated. The model may still recognize the general setup, but it may slightly soften the intensity because the most extreme recent analogues are still relatively sparse compared with the full archive. In this event, that possibility appears in the repeated tendency for the atmosphere to run warmer than guidance. The signal suggests not a breakdown in meteorology, but a tension between a fast-evolving physical reality and the long historical memory built into prediction systems. Surface conditions contribute strongly to this issue. Soil moisture, snow cover, vegetation state, and land use all affect how efficiently sunlight is turned into heat. If the land begins a spring period drier than older reference cases would suggest, then the same amount of incoming solar radiation can produce higher temperatures and lower humidity than a historically typical model expectation. A dry land surface reduces evaporative cooling. More energy then goes directly into warming the ground and near-surface air. This in turn deepens mixing, lowers relative humidity, and may feed back into the strength of the heat itself. Forecast models do represent these processes, but the quality of that representation depends on the initial land state information and on how well the model's surface schemes capture rapid transitions into very dry conditions. When the event is strong, even a small underrepresentation of land dryness can matter. The same is true aloft. If ridging events become more persistent or more intense in certain seasons or regions, then a baseline built across a longer historical span may smooth those changes into an average that no longer matches the most important operational cases. The atmosphere experienced by forecasters today may still overlap heavily with the historical atmosphere of previous decades, but the tails of the distribution can matter far more than the center when public risk is involved. Fire weather, heat stress, and infrastructure strain are often driven by those tails. A model that is excellent on ordinary days but a little conservative in the far tail can still leave important gaps in the warning chain during the very events that matter most. This does not mean that every strong heat event proves the baseline has become obsolete. Attribution at that level requires careful study across many cases, and scientists are rightly cautious. Weather varies naturally from year to year and decade to decade. Some apparent shifts turn out to be regional, temporary, or dependent on the measure used. Yet caution cuts both ways. It is also possible for operational systems to underappreciate a genuine shift if they remain too anchored to long records in which earlier, cooler conditions still exert strong influence on calibration. The scientific challenge is to preserve the stability that long records provide, while also staying responsive to changes emerging in the present climate. That balance is difficult. Long baselines reduce noise and protect against overreacting to short-term swings. But if the climate context is changing, excessive dependence on older averages can make today's extremes look slightly more surprising to the model than they should. This tension is part of why forecasters often blend raw model output with situational awareness. They look at observations, compare multiple guidance systems, watch real-time trends, and adjust for known biases under certain patterns. In a sense, human forecasting already compensates for the possibility that a shifting baseline may influence model behavior. When a ridge is strong, soils are dry, skies are clear, and recent days have come in warmer than forecast. Forecasters begin to treat the model not as a final answer, but as one voice in a broader physical interpretation. That practice is not an admission of weakness. It is a sign of mature science adapting to complex conditions. But it also reveals something important. The atmosphere may be changing in ways that make fixed expectations less reliable at the margin. The larger meaning of this event, then, is not that models can no longer be trusted. It is that their greatest tests may increasingly come from rare combinations of heat, dryness, persistence, and seasonal mismatch that push against older reference frames. A shifting climate baseline does not erase the value of the past, but it can alter how the past should be weighted when the present keeps pressing toward new extremes. The event shows this possibility with unusual clarity. The forecast sees the ridge, sees the warmth, and sees the danger, yet the real atmosphere still leans a little hotter, a little drier, and a little further into the tail than expected. That repeated lean is precisely what makes the question scientifically serious. The issue is not simply whether this one event was hard to forecast. The issue is whether the atmosphere is beginning to ask more often for answers from a system trained on a world whose most extreme edges are no longer quite the same. By the final stage of the event, the science arrives at its most careful boundary, the place where strong evidence remains intact but interpretation must become more disciplined. Much is already clear. The United States is experiencing a broad and unusually intense late March atmospheric pattern, marked by exceptional warmth in the southwest and interior west, major drying across the Great Plains, strong fire weather conditions, a pronounced upper-level ridge, an amplified jet stream, and a blocked configuration that slows the normal progression of weather systems. These are not speculative claims. They're grounded in observation, forecast analysis, and the physical relationships that connect pressure, temperature, humidity, wind, and land response. The event is real, the pattern is coherent, and the operational danger is measurable. Yet science becomes strongest not when it says more than the evidence can support, but when it separates what is established from what remains unresolved. This event demands that separation because it sits at the edge between immediate weather interpretation and larger climate questions that require wider evidence. What is known with high confidence is that the atmosphere can, under certain conditions, organize itself into a persistent pattern capable of producing simultaneous extremes across a continent. It is also known that strong ridges can inflate the air column, suppress clouds, intensify solar heating, lower humidity, and help sustain prolonged warmth beneath them. It is known that fine fuels in grassland systems respond quickly to low humidity and wind, and that repeated dry afternoons under a stalled pattern can transform a broad region into a highly flammable landscape. It is known that warm nights increase cumulative heat stress and reduce recovery for both human systems and natural systems. It is further known that forecast models, while highly skillful overall, can underperform in the most unusual setups when local amplifiers, land surface feedbacks, and persistence interact in ways that are difficult to capture perfectly. None of these conclusions require dramatic interpretation. They emerge directly from established atmospheric science. What remains less certain is how this single event should be placed within the longer evolution of the climate system. That question matters, but it cannot be answered fully by one episode, no matter how striking. One extreme event can illustrate a possibility. It cannot by itself prove a trend. Scientists therefore ask broader questions. Are patterns like this becoming more frequent, more intense, or more persistent over time? Are late season or early season extremes expanding their seasonal reach? Are blocking regimes changing in duration or structure in ways that alter heat and fire risk? Are forecasting systems underestimating some classes of events because the most relevant part of the distribution is shifting? These are legitimate questions, and this event gives them urgency, but urgency is not the same as final proof. To answer them properly, researchers need long records, careful attribution methods, model evaluation, and repeated comparison across many cases. The same caution applies to explanations involving the jet stream and high-latitude change. There is strong evidence that the Arctic has warmed rapidly in recent decades. There is also active scientific discussion about how that warming may influence mid-latitude circulation, waviness, blocking, and persistence. Some studies support links between a reduced temperature gradient and more amplified patterns in certain settings. Other studies find the relationship to be weaker, more seasonal, or more complex than early formulations suggested. The atmosphere is a coupled system, and large-scale flow responds to many interacting influences. It would therefore be too simple to look at one blocked heat event and declare that a single mechanism has been proven. The more responsible conclusion is narrower and stronger at the same time. The event is consistent with scientific concerns about persistence and extreme seasonal anomalies, but consistency is not the same as attribution. The evidence supports serious attention, not careless certainty. The same discipline is needed when discussing model limits. It is plausible that some forecast systems may slightly understate certain extreme heat setups if the most relevant analogues lie in the newer, warmer part of the observational record. It is also plausible that local land surface conditions, clear sky bias, terrain effects, and boundary layer processes explain a meaningful share of the underforecast without requiring a broad conclusion about climate-era model inadequacy. Both ideas can be partly true at once. Forecast error is rarely born from one source alone. It emerges from the meeting of physics, data, scale, and circumstance. What this event shows clearly is that underforecasting in a persistent spring heat pattern deserves close study. What it does not yet prove on its own is that all major future heat events will be underestimated for the same reason. Science must leave that distinction intact. There is also an interpretive temptation that extreme events often create. The temptation to treat coincidence as design. In this case, the heat, the dryness, the fire danger, and the unusual upper air structure arrive in the same broad window. That convergence can feel like a message, but atmospheric science proceeds by mechanism, not mood. If several hazards occur together, the right first question is whether they are physically linked through the same circulation pattern. In much of this event, they are. The heat in the southwest, the dryness in the plains, and the fire weather escalation do arise from a shared atmospheric arrangement, that is a real connection. Yet beyond that, science resists the urge to assign hidden purpose or grander narrative without evidence. The atmosphere can produce deeply unsettling combinations through ordinary physics operating at extraordinary intensity. That fact is sobering enough. What remains at the end is a picture both firm and unfinished. The event demonstrates how a rare springtime ridge can expand into a continental circulation regime, how that regime can lock into place, how local landscapes then translate it into heat or fire risk, and how forecasts can struggle when reality edges beyond expectation. It also leaves open the larger questions that only repeated study can answer. Is this event a singular expression of a volatile atmosphere? Is it part of a broader shift in seasonal extremes? Are present tools sufficiently calibrated for the tales of the distribution now emerging? Observations indicate that the pattern is extraordinary and consequential. It remains uncertain exactly how often such patterns may recur in the future, or which mechanisms will prove most important in explaining their persistence. That is not a weakness in the science. It is the science behaving properly, holding tightly to what is known, leaving space around what is not yet settled, and allowing the atmosphere to be measured before it is explained too quickly. The atmosphere settles now into a quieter frame, though the pattern it has traced across the continent remains clear in memory. A broad ridge rises over the western interior. Air sinks, warms, and dries as it descends. The land answers with heat. The grasslands answer with loss of moisture. Cities hold warmth into the night, and open plains wait beneath wind that can turn a small flame into movement across distance. Above all of it, the larger flow bends and slows, allowing one arrangement of pressure and air to remain longer than ordinary spring weather usually allows. What began as a map of unusual temperatures becomes a study in connection. The upper air shapes the surface. The season shapes the meaning of the numbers. The land shapes the risk that follows. Heat, dryness, and persistence are not separate stories. They belong to one structure, visible only when the continent is viewed as a whole. There is no need to force the event into a final lesson larger than the evidence can hold. It is enough to see what the atmosphere has shown with unusual clarity. A spring pattern can arrive with the strength of another season. Forecasts can approach the truth and still find reality leaning a little further into the extreme. A landscape can change character after only a few days of repeated sun, low humidity, and wind. Science remains steady here. It keeps what is known in focus and leaves what is uncertain undisturbed until more evidence arrives. In that steadiness, the event becomes easier to understand, not simpler, but calmer. A rare arrangement forms, holds, and reveals the physical links between sky, land, and time of year. Then the mind can let the pattern rest, not as noise, but as one more carefully observed moment in the long atmosphere above the continent.